right. Well, we don't seem to have many people here.
Yeah, let's see if we get anyone else.
All right, we have the recordings already started. I'm Harry Ricker. This is the Cosmology discussion group meeting for August 17th, 2025. And actually, I think that this proposed topic, I wanted to make some preliminary remarks, is something that probably people need to know more about, given the discussion that we had yesterday, which I thought was pretty confused. And when the topic of methodology came up, that caused some commentary. I noticed. I don't know if you saw that, Robert.
I saw most of it. I didn't see
And
everything
he declared
yesterday.
that he thought that the correct method was the math had to be right, and then it had to be matched up to experiments correctly. That apparently caused some controversy, which didn't really surprise me at all.
Yeah, I sort of take a holistic approach there, because one thing works on something else, and it tends to go around in a circle.
Right. Well, I've studied this topic rather thoroughly, and my favorite philosopher on this topic is Feyerabend, which I'm sure you're familiar with, who wrote this book on method where he claims there is no method.
Fire Robin, yeah, against method, yes. He was actually a student of Popper's.
Right, and I noticed you didn't really mention Popper.
I do actually. I'm somewhat sympathetic with Popper, but I don't think it's the whole story. I
Okay.
I kind of combine together confirmation and refutation.
I think the conclusion that one would come from the discussion of yesterday was that scientists don't obey the scientific method, even though they claim they do.
That's also possible. There's just a whole range of things, but
Yeah, well, trying to have I don't think adherence to the scientific method is something I think they pretend to. I'm not really sure they really do.
mhm.
Anyway, so we can have a discussion on this topic. It's a discussion which I find interesting. I'm not sure that other people do. But anyway, you can go ahead and start if you'd like.
Okay, let's see if we can get my slides up. I think you have to make me be the.
Well, you have to request a share. You have to do a share request.
Oh, okay, under share. See if this does. Send request. Okay.
All right, I've approved it.
Okay, let's see. What do I hit next? You just have to remind me. Under the share?
Yeah, you go to the share screen and then you want to click on your presentation.
Okay, here we go. Did it come up?
Yes,
Okay, everyone sees it?
I
Yes.
see it.
Okay, I'll go
You can
reasonably.
make it a little bit bigger if you can.
Let me see. I can try slideshow if I can. Let's see. Some
Nothing.
current
It didn't
slide.
help.
Did that work?
Oh, okay, there we go. All right.
Okay.
All right, that's good.
Okay. Yeah, I actually have a PhD in philosophy from Boston University. And actually, that philosophy department's moderately well known for their Center for the Philosophy and History of Science. And I've known any number of people there, including my thesis advisor, Abner Shimoni, but also the ones who were heads of it. They were actually Marxists, but Bob Cohen and Mark Swartovsky, and they had a whole series of books on, uh, well, pretty much the philosophy of science. So we also had Joe Agassi there, and he was a student of Karl Popper. So I've had some background in this, and it seems to me, particular over the last month or so, I'm not sure maybe Jerry sort of started the process, but it wasn't just Jerry. But we had these real long email streams, some like going back and forth over 100 back and forths. And some kind of got kind of nasty in the process. And like people were arguing past each other, and it wasn't really clear that any progress was being made. So I thought maybe like taking a step back and looking at the scientific method a little bit. And I use this in a pretty broad sense. It may be for normal science, it may be looking for new theories, it can even be for testing uh, theories in metaphysics. And what I say, it's fairly mainstream, at least for the most part. And it really involves a combination of a couple of different approaches, both stressing theory confirmation, which is like Hempel's approach, and also theory disconfirmation, which is the approach of Karl Popper, who said basically the definition of science is that its theories ought to be falsifiable, and said the stress should be on falsifying theories rather than on confirming them. Actually, I think you need both. Okay, but let's move on to the next slide. See if I can get these to work right. Okay, problem. The Quine-Duhem thesis. Duhem, that's Pierre Duhem, who wrote a book, The Aim and Structure of Physical Theory. Quine was a philosopher at Harvard. Actually, I've met Quine. When I started out at Boston University, I was a teaching assistant for George Berry, who was a logician, but he was also Quine's first graduate student. And Berry also had a Quine seminar. In the last session, he would always invite Quine over. Quine's a very well-known philosopher, and it's actually in his paper, Two Dogmas of Empiricism, and this is actually with the second dogma, not the first. The first involves the analytic synthetic distinction, but the second involves reductionism. And the Quine-Duhem thesis is it's always possible to save any non-contradictory hypothesis, no matter how bizarre, if one is willing to make enough adjustments in other assumptions. Uh, and this is true as far as I can see. If anyone's ever had a conversation like, oh, with someone who is mentally ill, like someone who's maybe schizophrenic or delusional, and I've had some experiences in dealing with people like this, they can hang on to any uh, claim, no matter how bizarre it is, by making other adjustments. Like, well, this actually involves my sister. I don't want to go into it in any detail, but she claimed to have gone to her wedding in Hawaii. She she went to Hawaii. She kept claiming the wedding had occurred, but even afterwards, by saying that she could go backwards in time and stuff, and so she could hang on to that claim no matter what. And so it's true. You can hang on to any claim no matter what if you're willing to make enough adjustments in other areas. And I think this happens sometimes in science or pseudoscience, including some kind of reputable claims. I don't know about UFOs or about like oh, tarot cards or and if you just keep making enough other adjustments, you can hang on to your account. Uh, Thus, there's a battle to determine the best explanation among competing theories in accounting for known intersubjective experiences. By subjective, I mean what goes on with our phenomenal experiences in our conscious mind. Intersubjective means where different people have at least roughly analogous experiences. And so we want to hang on to the empirical account. Empirical is a reference to what happens with our sense experiences. And we can call this empirical adequacy. So that's a constraint. I mean, and the reason for having it be intersubjective, I mean, you could always have like individual experiences. They could be like oh, hallucinations or like eye spots and things, which just don't correspond with anyone else's experiences. But when more than one person has similar experiences, then we can have, say, it's intersubjective, and we need an explanation as to why this is the case. Maybe one other point here on Quine. Quine actually changed his position. Originally, he would, by experiences, he was talking about sense data, but he kind of switched to being a materialist, and he ends up talking about what occurs, stimulus impingements on our sense organs and things like on rods and cones of the retina as being what he means by intersubjective. I don't buy into that. I think the conscious mind is something distinct that's reconstructed in some way from the brain. Okay, but in any event, that's the problem, the Quine-Duhem thesis. And now
Okay,
I'll go.
Bob, could you tell us a little bit about Duhem?
Duhem was a French Roman Catholic priest. I've got his book. A lot of it sort of gets into Aristotelian science and things, which of course is popular with Catholics. I was hard pressed to find the relevant section in his book. I looked at Quine's paper. He refers to the French edition, and it turns out the English edition only came out after Quine's paper. So, finding a particular passage in this where he states the thesis, I found was kind of a difficult thing to do.
Yeah, I know. I've read that book too, and that's why I brought this up because I'm as you are. I was hard pressed to find it in Duhem's book, but it's become how should I say it accepted to refer to this as the Quine-Duhem
Duhem
thesis.
thesis, and
But I
Quine
think
does
Quine
refer
is
to.
actually more responsible for it.
I would tend to agree there, but he does give a reference to Duhem in his paper.
Okay, but that's very good explanation, I think.
Yeah. Okay, let's see. Okay, the hypothetical deductive method. I think most people in philosophy of science hold some version of the hypothetical deductive method. The only kind of a little bit of a controversy is when you're doing real normal science and you're just trying to repeat an experiment and things. You maybe aren't at least all that interested in new hypotheses, but try maybe just to confirm something that's already out there. But for actually testing a hypothesis, I think something like this is true. I cite Karl Hempel. He was at well, he was originally European, but he was at the University of Pittsburgh for a long time. And the University of Pittsburgh, like Boston University, had a center for the philosophy of science. I guess it still does. And I also mention Karl Popper. Logik der Forschung is the German for his book, which originally came out in 1934. But in any event, the idea is here, hypotheses can be formulated by any method whatsoever. They may involve a generalization from observations, but not necessarily. But the idea is once you have a hypothesis, to try to test it against empirical consequences, which may involve, basically the way I look at it is an actual experience in someone's mind. And I want to talk about two cases. The cases where you confirm the hypothesis from, okay, the arrow there, it's for a conditional statement, which is an if-then statement. So if the hypothesis is true, then the empirical consequence is true. Let's say the empirical consequence is true, and if you try to infer, therefore, the hypothesis is true, if you take this to be a deductive argument, it's a fallacy, the deductive fallacy of affirming the consequent. And I mean, the problem I think is fairly evident. There might be another hypothesis which has the same empirical consequences. So it's not really adjudicating among the different hypotheses which have the same empirical consequence. So you can't infer that your hypothesis is true. The second version, which Popper likes to emphasize because it's logically valid, is theory refutation. If the hypothesis is true, you have the empirical consequences. The empirical consequences don't occur, therefore the hypothesis is false. If you keep this as the simplified version I have right here, this is a valid argument. It's known as modus tollens, the backwards method. Okay, but there's more to say. There's actually more to say in both cases. So I can go into both cases in a little bit more detail, starting with theory confirmation and then with a theory refutation. Okay,
Okay, could
here's
you explain that notation a little bit?
the one back here.
Go
Okay, this
back
is
to the yeah, what does E mean? And you said you have X arrow E,
well,
E,
it's H.
therefore,
H is the hypothesis. E is the empirical consequences or a prediction.
okay, so you're
Uh,
saying the hypothesis implies
Empirical consequences. If the hypothesis is true, then the empirical consequences are true.
and then the implication is that the hypothesis is true. Okay.
That's right, which is a logical
And then
fact.
the alternative or the opposite is the hypothesis implies an empirical result. The empirical result is not true, therefore the hypothesis isn't true.
That's right.
Okay.
That's the notation here.
You will recall that we discussed the first of those when I was talking about the redshift and so on. So the error here was the hypothesis would be that a Doppler, sorry, an expansion, a relative motion of objects um, would leading to a Doppler effect would give a redshift. But the error was therefore, we know there's a redshift, therefore H. Well, that isn't the case. That's contravening this because there are other possibilities of
Right, exactly. So you can't make the inference,
right.
at least as a deductive argument. My next slide is if you switch to interpreting this as an inductive argument. Induction, at least as logicians talk about it, you give some support or probabilistic support to your conclusion from your premises, but it's not conclusive support. Uh, okay. So here's my slide on it. Theory confirmation can to some extent be vindicated by using the concepts of coincidence and probabilities. Okay, coincidences are cases where two events are paired together without being causally linked. For example, oh, let's say you're tossing two coins and they both come up heads. Well, that, probably the fact that they're paired together is just a coincidence. You keep tossing them, say, 100 times, and they keep being both heads for the 100 times. Well, sounds like there's something else going on. Maybe they're loaded coins or something, but it sounds like there's something else going on, and you want to examine the possibility that there is something else going on. Okay, so the concept can both be applied to cases of physical causation, like coin tosses or maybe tossing a dice, and also to more, well, abstract matters, such as theory confirmation. Uh, yeah, I mean, it's a basic claim in science that science has to be reproducible. The results have to be reproducible. If you have a problem reproducing them, then it means there's something gone wrong. Maybe it just happened to be the case coincidentally that when you ran the experiment, you got the certain result, and if you can't replicate it, then yeah, you can just explain it away as being a coincidence. Thus, successfully repeating an experiment, particularly in independent laboratories, decreases the probability of its initial success just being due to a coincidence. Uh, and I bring in Bayes' theorem here. I don't know if I have to go through it in detail. It's a well-known theorem. I find different books even state it somewhat differently, but they all involve the concept of a prior probability and a posterior probability. The prior probability is the probability going in. The posterior probability is the probability once you've had the confirming instance, which obviously is going to raise the probability of the theory being true. So the final probability here, it's sometimes called a conditional probability. So conditioned by the outcome of your experiment, which is in accordance with the prediction, it increases the probability of the theory being true. Now, what gets a little bit controversial here is the concept of a prior probability and where it comes from. As far as I can see, you ought to give it a finite amount, even a very small finite amount, for almost anything, maybe including the truth of astrology or something. If you keep repeating and you keep being successful, it means that there's something to the theory that's making it come out true, having successful predictions. But it doesn't, again, necessarily mean that the reason is the theory is true. There can be other things going on, and I mention a few of these. In the case of physical coincidences, a couple of things to watch out for: a common cause, something causing both events, which is responsible for both events, or reversing the cause and effect. You get the cause and effect backwards. Maybe an example might be like an illness that has more than one symptom, say a common cold with a sore throat and a runny nose. And if you say the runny nose is the cause of the sore throat, or well, or be like other symptoms, you can throw in a fever or something. What you're saying is one symptom is causing the other, and whatever the root cause of the cold is actually causally responsible for both symptoms. Now, you might run into something similar in the case of theories and confirmations. If there's something that's responsible both for the existence of the theory and the confirmation, responsible for both. I don't know if I have a good example right offhand, but that would certainly be something to watch out for. The other thing is if you have things in reverse, and this can certainly happen when you have a well-known scientific phenomenon and you come up with a new theory to account for it, and yeah, you can predict it from your theory, but maybe the reason you picked that particular theory was just because it does have that as a consequence. So there, you would in fact have the reversal of the two, which is why it's always more impressive when you have a novel prediction rather than one which is already well known. Uh, I mentioned a couple other problems here, the tacking problem, where you can tack on just more content to a theory than the original one and say that it's also confirmed because the empirical consequences are in accordance with it. Some sort of a solution there is to give minimal content. The other one is verisimilitude. Actually, Popper talks a fair amount about verisimilitude, which is the closeness to truth. So maybe the theory that you confirm is sufficiently close to the truth, say Newtonian mechanics is sufficiently close to the right theory of gravity that you get like the right planetary orbits and things like this, but maybe it's not completely true if you claim that general relativity is a superior theory to Newton's theory of gravity. So there, the theory is good enough that you can give it gives a good prediction, but it's nevertheless maybe not the complete truth, or it may be technically false, but approximate the truth close enough. Okay, so that's a theory confirmation. Next, I have theory disconfirmation, and here I add in a complication. And the complication involves what are known as auxiliary hypotheses. So instead of just H, therefore E, we have various other hypotheses that you actually have to invoke in order to make your deduction. These include laws of physics, ideal laws, not necessarily as we know them, various initial conditions, in other words, descriptions about like the way in which an experiment is set up. Ceteris paribus clause is actually for things being, you say things being the same, all things being equal, and maybe those could be questions. And I throw in here also assumptions about the competence and or integrity of the researchers. And it's not completely unknown for people, if enough pressure is put on them to get a certain result, to just make up data. Sometimes someone just doesn't have the laboratory skills, and there's the danger there of what's sometimes called cherry picking data. You pick out the results you like, you throw out the ones you don't like. So these are various assumptions which are being made. In which case, with the logic, I use the ampersand for a conjunction for and. So given the hypothesis and these various auxiliary hypotheses, therefore the empirical consequences, here, when you run the experiment, it's not in accordance with the prediction, therefore not the case for the whole conjunction. And then in logic, there's a rule known as De Morgan's rule, where you change a conjunction to a disjunction. A disjunction is the word or. So that top one is equivalent to not H or not A, or A1, or not A2, or not A3, and so on. So you can't necessarily infer here the falsity of your hypothesis. You just have to infer, you can just infer that either the hypothesis is false or one of your auxiliary hypotheses are false, in which case they can be examined individually. So the merits and demerits of the individual auxiliary hypotheses can be examined individually, and if they hold up, an inference can be made that the hypothesis being tested is false. Okay, so that's theory disconfirmation. Okay, next, postdiction versus prediction. Okay, postdiction is very common. Here we know a result, maybe we don't like the theory accounting for the result, so we come up with a new theory, and lo and behold, we get the result. But confirming cases of theory prediction are always more impressive than cases of theory postdiction, since cases of postdiction can always be seen as cases of constraints on theory production from known facts. We already know what we're looking for, and so we just pick a theory which gives those consequences. But for prediction, I give a few here. Maybe some other people know some better ones. Cases, let's see, Adams and Leverrier's prediction of the planet Neptune from known perturbations in the orbit of Uranus. Poisson's prediction of a bright spot in the shadow region from the wave theory of light. That was one of the big confirmations of the wave theory of light. Wolfgang Pauli's account of properties of a particle, a predicted new particle, the neutrino, some 20 years prior to its discovery. Some people might throw in here, like the case of the change of a position of a star during a solar eclipse for confirming Einstein's general theory of relativity. Yeah, but in those cases, I mean, it doesn't necessarily prove the theory, but it's certainly more impressive when the theory makes a new prediction. You could also bring the concept of a crucial experiment here. When one theory makes one prediction, another theory makes another prediction, and when you run your experiment, it confirms one theory and not the other, which shows that, again, not conclusively, but it's certainly pretty good evidence that the first theory is true, and the second, even if it's a well-established theory, is false. But again, you need to repeat things in any number of points. Okay, postdiction versus prediction. Fallacies to avoid. Yeah, I've taught informal logic any number of times, and the textbook usually has a section on informal fallacies. They're not logical fallacies. Some of these are very common, and it's not just in ordinary life. They can occur in science as well. Unfortunately, I mentioned three. There probably are others here. intimidation, maybe the head of a laboratory, and this can actually happen. They very much want to be able to publish a paper. They want results. Threats or bribes, both variants on both can occur. If you want your job, you better come up with the data we're looking for. Bribes, might be a monetary bribe, I don't know, but this is known as ad baculum or appeal to force. The second one I have is authority. Someone has a big name, maybe Einstein, maybe someone else, maybe Newton, I don't know. And we say because they make a claim, therefore the claim is true. This argument actually has some force, but there are things to watch out for. And the person has to be a genuine authority. They can't just put up a degree behind their name, maybe a made up one, or from a university where you can just buy degrees or something. So they have to be a genuine authority, making a claim within their field of expertise. Maybe someone is famous in one field and they endorse a product, and here, of course, maybe also be a bribe, since they take money for the endorsement. But you hope their fame in one subject rubs off on another subject. And it also has to be an area, not an area where the experts disagree. And this can obviously happen sometimes. You got, I know sometimes in a trial, various medical experts may be brought in. The one for the prosecution says one thing, the one for the defense says something else. And who's the jury supposed to believe? Well, just the fact that the person has an MD doesn't really decide the matter since both do. So that's also something to watch out for. Also, the argument against the person in Latin is known as ad hominem. Can be abusive. I've run across this before. You just attack a person personally, and you use abusive language and things. That can happen. Circumstantial, that has a couple of different variants, but there's something about the person's circumstances. Maybe like they have a conflict of interest. They have something to gain or lose by making a claim. Yeah, so you attack the person based in that case on the conflict of interest. But I'm saying here in science, we want to do it on its merits, not necessarily on the people making claims. Though to some extent, I mean, if someone, I mean, if there's a problem with maybe some of their work, maybe they're not that good of an experimenter. Maybe they've been caught in a scandal of some sort. It's something probably that it could be relevant, but often this is just made by someone on the other side. It happens in politics all the time. One candidate attacks another candidate, not really on merit, but based on any number of ways of detracting from them. Okay, so those are some things to avoid.
All right, we're coming up here with 5 minutes. Do you want to stop here and um, uh, uh, pause for comments and questions? Or
Yeah, maybe. Okay, why don't we do that? And then
we're
I
getting,
think I have like three more slides, but okay, yeah,
well, I think that would be better rather than having you get interrupted.
yeah, sure. Okay, yeah,
Okay, go. A couple of things that to the previous slide, a couple of big issues that bring to mind. Go to the previous one.
previous one.
Well, actually, both of these slides. One of the big issues in climate change, which is the big argument today, is that none of their predictions have actually come true. Are you familiar with this argument?
I'm familiar to some extent with climate change, and one trouble is this can happen in other areas also, where politics
Right.
gets mixed up with science, and it's very hard to separate the two. I know the two happened with COVID also. And I don't think I want to take sides on either one, but I might agree with you that in both cases, politics got mixed up with science.
Well, to me, they keep talking about predictions, but their predictions don't ever come true. Okay, and this is kind of one of the things this recent report that's been put out where they get into that issue about what is it, what is the actual, what are the predictions and what does the actual experience show? Well, they don't match up. That's kind of the point that this recent report has come out with. And so you kind of wonder, you know, how can you do science and claim that you're correct if your predictions, you know, don't match the data?
Right. And of course, an added wrinkle there is that this predictions tend to be statistical, and it's much harder to refute or confirm a statistical prediction than one that's not statistical in character. And of course, with weather, I mean, it's all over the board. So the fact that one year was warmer than the previous one, you kind of have to look at trends and things. But yeah, yeah.
Well, their approach is basically they look at a lot of the different predictions and show that apparently almost none of them turn out to be correct. Okay,
Yeah,
so we
that's
could
right.
go to the next slide. And I think that the issue is this authority argument where the whole basis of climate change is based on the authority argument.
There may be some.
97% of climate scientists agree that climate change is real.
Right, that's interesting because you, Bob, are there in the second point about an authority talking about some subject in which he's not an expert, let's say. But I think
Yeah.
you're talking, Harry, about a common thing where an authority is speaking on a subject on which he is an expert. He has qualifications and degrees, and therefore it being accepted. So I suppose there are two slightly different aspects there, are there not, Bob?
No, I agree. There are lots of subtleties here, or there's sort of an intimidation business here off of authority sometimes. Someone doesn't want to question an authority just because they are an authority. And who am I to question the person, particularly for a big name? Yeah,
Well, there's the intimidation aspect too, because this fellow from University, what is it, Penn State, went around suing people who disagreed with him.
hmm
There's
That's
some,
the threat part. Yeah. Well, the
so
broad
he,
part can also occur.
so I mean, yeah, so if you don't like if other people criticize your theory, you sue them.
hmm
That's I think, part of the intimidation aspect of it. So those are a number of
Oh, it
fallacies.
also can be if you want to keep your job, then we want results, so we better come up with the results you want.
Well, there's a lot of that, yes.
Well,
Okay,
it
getting
can be subtle as well. I mean, it doesn't have to be an outward intimidation. We just find in history that people who have questioned some of these aspects never progress in their careers. They haven't been deliberately threatened, but the results are that they never progressed.
Yeah, it can be publish or perish. Yeah.
Or there, what about the lady that was showing that the polar bears are doing just fine, and she was fired from her academic position?
Yeah. Okay.
Well, we can point to a lot of examples of I don't think this whole business of climate change, I don't think that's science. I think that's the conclusion that you really ought to come to. It's not being handled in a proper, according to your methodology requirements, Bob, right?
hmm Yeah. Although I didn't give a separate slide for statistical arguments. I mean, if you want one sort of on the other side, I'm aware of this one. Ice on lakes. Ice on lakes actually has been getting thinner. In the Netherlands, they can't skate on their canals anymore and stuff. I live on a lake, and the ice has been getting thinner here. I used to be able to go for miles out on some of the Great Lakes. You can't do it anymore. Uh,
Yeah, but that doesn't necessarily mean that
I know, and you can have cycles and things. So the whole thing you got to be careful with. I'd be the first to agree with
all
that.
right, we're coming up to the end here. Less than a minute. We're going to cut off here.
Perhaps a fallacy to avoid additional.
Interrupted there, Jim.
Oh, thank you, Harry. Yes, perhaps an additional fallacy to add to that slide might be the democracy versus science. Like when we say, when the propaganda says that 97% of meteorologists believe in climate change and so forth, that actually we don't, in science, we don't evaluate the veracity of a theory or hypothesis based upon taking a vote.
That's right. That's sometimes called ad populum, appeal to the people. And of course, the average person, they may have
Bring
no
in the
expertise.
Latin. I love it. Thank you. Thank you, Bob. Bring
Okay,
in the Latin.
we need to put your presentation back
Okay,
on.
I think we're going to have to do this again. Let's see.
Great presentation so far, Bob.
Okay. Well, okay. Yeah. Okay. See, send request.
All right, I want to go back. I brought up the issue of climate change, but I want to talk a little bit about relativity and some of the
Okay. Let's see. You want the slides back up?
aspects. Yes,
Okay. Let's see. Let's see if I can do
because I
it.
think a lot of the issues that you're talking about are relevant to the discussions that we have about relativity.
Oh, definitely. Definitely. Yeah.
Now, I don't know whether you prefer to do it at the end, maybe,
Well,
or
why don't I finish this? And there were some things on relativity that,
Well, could I just mention quickly, gentlemen, that your first slide, I think Bob said, the method you were talking about, um, that you can introduce new parameters or whatever, the way you expressed it, you change the variables for any non-contradictory theory. But presumably it's being done for contradictory theories. In relativity, for example, I think most of us would consider, say, the twin paradox is a contradiction, but they introduce, they change the variables so that even this contradictory theory is rendered ostensibly acceptable.
yeah, yeah. Yeah, I mean, not everyone agrees that that's a contradiction, but that one really ought to be sorted out. Really would help if some of the relativists would talk with some of the dissidents. I don't know how many times I've come across that where I start a conversation, then they just don't want to discuss it. Although I
yeah.
do have a brother who likes special relativity, and I've talked with him on some of these things.
Um, okay, why don't I think you said you had 3 slides, so
Yeah,
why
okay,
don't we
let's go on to his
continue on
slideshow again.
and then we can talk about some of the issues of application.
Okay, slides. Let me see if this will do it.
Well, it's already up here. I see your presentation.
Yeah, okay, let's see. We're from current slide. Okay, here we go. Okay, yeah, I'll have to go through these. I'll see. Okay, meta methodological issue.
Excuse me.
Okay, first, I guess what you were just talking about. Avoid contradictions. And I used to like Niels. I like the early Niels Bohr, but not the later Niels Bohr. I liked his original model of the atom. The Copenhagen interpretation. He just embraces contradictions. Particles, they can both have waves like on one day and particles another day, without trying to work with the concepts to get something that has both wave properties and particle properties, which is one of the things I've worked on. Then you can bring in relative simplicity. It turns out simplicity is not an easy thing to analyze. I know as an undergraduate, I went to Dartmouth College, and the president at the time was John Kemeny, who actually originally worked in philosophy of science at Princeton. Then he moved off to the math department at Dartmouth, and he actually wrote the computer language BASIC. But he had some papers on simplicity and also on reductionism, and he did it in terms of the complexity of a mathematical equation, a linear equation would be simpler than a quadratic one and things like that. And I also bring in Nelson Goodman, who was also at Harvard. He was an idealist, whereas Quine was a materialist. But Goodman wrote on the scientific method, and he has a very famous paper on GRU, where something is green up to a certain time, and then the concept is it's blue after that time. And so you take all emeralds are green, and up to a certain time, you have all this confirming evidence, and you say all emeralds are green, and the next time you make an observation, and it's not green because it's still green and hasn't changed over to blue. But he just uses that single concept. So in terms of like the concepts being used, like how many letters the concept has or anything like that, it's just not going to work. So coming up with an analysis of simplicity, I think I can say at a minimum, is not an easy thing to do. I mean, it sounds nice. And I think we have an intuitive like a grasp of it, but giving an analysis that really holds up isn't easy. And I also point out that
Is this idea related to Occam's razor?
well, Occam's razors don't multiply entities beyond necessity, go with the simpler. Yeah, it is related, but again, the question is how you analyze what's simpler. And I make a point on the mathematics also here. Like mathematicians, and I find physicists, they tend to be good mathematicians because that's the way they get ahead. They get good grades because they can solve the homework problems and do the tests because there's a lot of math in them. And so, like with time, you put a negative sign in front of t, and yeah, it's just about as simple, and you come up with a nice account mathematically. But what does that mean conceptually? Like for time to go backwards in time. And I know there are theorists who talk this way. There's some versions of quantum mechanics interpretations that have particles go backwards in time and then forwards in time and things like this. And as a calculating device, fine, but as for a model of what's actually going on, I find that problematic. Or action at a distance. It's no problem describing that mathematically, but saying again that you can have a cause and effect, the immediate cause here, with the immediate effect being at a distance apart, it's not clear conceptually how that is possible. So yeah, those are at least some issues to try to tackle. Let's see, my next one. Research programs. Actually, even Popper talks about research programs. He doesn't use the same language as Lakatos. It's usually associated with Lakatos. So a research program, here you kind of bring in the holistic approach. You don't test a theory or part of a theory individually, individual hypotheses. They do not consist of just of individual hypotheses, but rather a coherent system of hypotheses together with an empirical testing program. And I think, in fact, if you look at the way in which science is done, it does involve research programs, in which case you can distinguish between two types, a good type and a bad type. Although there might be some disagreement about which theories belong to the good type and which theories belong to the bad type. The good type is the progressive research program. These are characterized by accounting for known empirical facts in a non-ad hoc manner, where you don't just tack on something to the theory in order to make account for something new. And exposing the theories to falsifiable predictions. Popper emphasizes this, making bold predictions and see whether the theory still holds up, together with running relevant experiments and accepting the results as they go against your theory. So those are the progressive programs. The regressive programs, they're characterized by ad hoc additions to save theories from refutation. Different variants of a theory are emphasized depending upon what one is trying to explain. If you like, I think I might pick on special relativity there for a second. I know, like, I've done some work, like, with entanglement, where you have these correlations at a distance. And Shimoni, my thesis advisor, he was one of the first people to work this off of, to show that Bell's theorem has empirical, as something you can run in a laboratory. And every time they ran it was in accordance with quantum mechanics. Yeah, here. Shimoni's way of saving like special relativity was to say you couldn't use the correlations to send a signal. And there actually are some theorems that say you can't use it to send a signal. Nevertheless, there has to be something causally responsible here. And if you have a space like separation between the detectors, like with aspects experiments, Aspect got a Nobel Prize for this, then it would seem like there's something that is responsible. But it turns out for other variants of special relativity, ways of interpreting it, like people talk about the block universe and things like this, where it's not subjective in the sense of emphasizing like the role of signals, then yeah, maybe you account for something else. But if you just pick the variant that you like for a certain set of predictions, then it turns out the theory isn't really just one theory. It ends up with different variants, and you bring in the particular variant that works best for your account. So again, that would be, to me, a mark of a regressive research program rather than a progressive version. But I think Lakatos is basically right that what we're testing is not so much individual hypotheses, but whole classes of them. And Quine would agree there also. It's the whole system. Okay, so that's the concept of a research program. And you can never really conclusively refute one or confirm one or prove it's true, but you can show that it's either progressive or regressive. And then let's see. Yeah, I have a final slide here. Suggestions for a way forward, because it's not real clear maybe how progress is to be made here. We just have these competing research programs out there, and who's to say which one to hang on to? Okay, so maybe some more could be added here, but constraints on theories should include logical consistency and accounting for known empirical intersubjective facts in a non-ad hoc manner where you don't just tack them on. Some version of physical realism should be accepted. I'm a physical realist. There are some people who say that the business of science is just to link to various predictions of empirical content, observations together without, Quine's language here is an ontological commitment. Ontology is the study of existence. So you say that your only commitment to something existing is maybe the observations. Positivists, logical positivists tend to say something like that. Ernst Mach, for example, was a logical positivist. But I think really that there's an awful lot to be said for physical realism, and it's something separate from observation. Atoms, we don't observe atoms. I think there's an awful lot that you can explain by taking seriously the claim that atoms exist. Chemistry, I hear. You can't really do chemistry if you don't say atoms exist or electrons exist. Light exists, although how it exists may be a good question. I'm satisfied fields, the electric field, the gravitational field, that they exist in some manner, but maybe we're not clear on how. So I think some version of physical realism should be accepted. Recognize that the concept of there being an objective truth out there is different from claims to know that truth. It's just arrogance to claim that we have the final theory and know our theories to be true. But people sometimes confuse the issue of knowledge from that of truth. I'm satisfied there is a truth out there, but with science, we're trying to learn about that truth, and we may or may not succeed, but it's a separate issue. Recognizing that we never gain certainty in the physical sciences. And because we never gain certainty, that a certain amount of tolerance should be given towards researchers utilizing a different approach from one's own. I wish that people working in special relativity, there's nothing wrong with working in special relativity, but I think they should also listen to dissidents. And finally, that constructive discourse should be encouraged among people whose theories have enough in common that such discourse is possible. If there's nothing in common, you really have nothing to discuss. But if there's something in common, then you don't have to do all the work by yourself. You can get some other people to work with you and maybe make some more progress. I wish you had more people who are interested in my particular model, for example. But in any event, that's the end of the presentation. See, people have questions, or we can go back to any particular slide if people want to.
Interestingly enough, the last bullet there can be contravened very often because people, non-specialists, are frequently surprised to see that people who are almost in complete agreement from their point of view are the most radical in attacking each other's theories.
Hmm. Well, that can definitely happen. People will hold very similar positions, but they disagree on something else. And sometimes, yeah, you can get ad hominem and a number of things occurring.
I might even dare I go so far as to say that I've observed this among us dissidents, in the
We're
CN.
no better. We're no better. I'd be the first to
Yeah,
say.
yeah, quite so.
See, other people have comments or questions? Let's see. Jim? Huh? Let's see.
Okay. All right. We sort of have quiet here. Nobody's saying anything. I muted myself because I was coughing. Okay. Well, thank you. Um, does anybody want to broach any subjects? Okay.
There's one question, very simple one. It's a theoretical approach. I do like it very much. Maybe I didn't understand 100% because there are some notions I am not aware about it. Philosophy is a little bit far away from physics, and I'm a physicist. Can you analyze through the prism of your presentation today some theories, suppose the Big Bang model, how it looks like according to your scientific philosophical approach?
Okay, the Big Bang model. Okay, the universe had a beginning, the Big Bang, which I guess is the majority opinion. Yeah, okay, that's the theory. Then you try to make predictions. And I know one that they actually did use there is the redshift, and where there's a bigger redshift, the more distant the object, like with Hubble's law. Okay, so I suppose that would be an empirical prediction. And the question is, I mean, like, well, alternative hypotheses. And I do know there's some out there. There's a tired light one, I think is one we ran across. There may be other ones. So it certainly doesn't prove the truth of the Big Bang that we observe a redshift. Yeah, okay. Yeah, so you can use this. You can use what I'm talking the general method actually all over the place. But yeah, that would be an example.
Let me bring this topic up, which is the general theory of relativity produces multiple predictions. Okay. Lots of different predictions. The universe could be expanding. It could be static. There's a lot of different models of the expanding universe. So since there's different predictions that could be derived from the general relativity, why would you think that that confirms anything? The fact that it makes a prediction that's confirmed by measurements.
Yeah, you talking about different variants on the theory or just the theory
No,
itself?
the general relativity is based on a differential equation which has numerous different solutions.
Oh, I see different solutions.
Well, isn't the cosmological constant one of these adjustable parameters, or dark
Correct.
matter, if you wish?
Correct. There's that's a what I think you would call an auxiliary hypothesis.
Yeah, okay. Yeah, but it also sounds like within the theory, there are the different variants with the different solutions.
Right. So the supposedly the argument goes something like this. Because the universe is astronomers see that the universe is expanding, that confirms the hypothesis of general relativity is the applicable theory. And then general relativity, when you work back the differential equation, you have a point in time where everything has to be there. There's a point in time which is the initial condition at which the universe starts. Okay. So that initial condition is the Big Bang.
Right.
Then now you have this additional empirical thing, which is the cosmic microwave background radiation. Okay.
Right.
And so then so they said Alper and his associates came up with a theory that said we can predict this microwave background radiation thing. And then when they actually measured it, they said, oh, great. That proves Big Bang is true.
Well, it doesn't
I
prove
talked,
it's true.
I
Also,
talked
I think
about,
that's a case of post-diction. Since my understanding with the background radiation, they made the observation first. I think it was from a couple of people working at Bell Labs in New Jersey. And then once they knew about it, then they had these various accounts of it. So I think it really is more post-diction than prediction.
right. Now, that's an interesting issue that we can talk about. Now, I know that Assisi, are you familiar with Andre Assisi? I think he's a Brazilian guy. Now he recently put out a um, link to a video that he's done where he talks about how there are numerous predictions of the cosmic microwave background prior to Alper and Gamov making this prediction, and that the Alper prediction was completely wrong, and some of the earlier predictions were much closer to the truth. And he's questioning this whole idea that the microwave background radiation proves the Big Bang or confirms it.
Yeah, I'm not familiar with him, but yeah,
Well,
that would definitely be a point to make. Yeah.
the point is that he's assembled all these prior predictions of a microwave background temperature, if you will,
Hmm.
a temperature of the universe. And the most well-known one is the one in 1939, where it has to do with these molecules that I forget the name of the molecule that they were detecting the radiation from this molecule, and from that they inferred that the temperature had to be, in order for these transitions to be observed in this molecule, that there had to be a temperature of the universe, a background temperature, to cause this molecule to be excited into these states. And they calculated the temperature, and I think it's something like 3 degrees Kelvin or something like that. I think I talked about that in one of my talks previously here. So we lost Bob somehow.
No, we'll start.
Huh? Where Bob went away.
We can talk without him.
Okay, well, my point is, so he was saying that's an example of post-diction. And so the question then is, which prediction do you want to pick? The one that was done by Gamov and his group, or the ones that were done before that? That's the issue that Assisi is raising. Has anybody seen that video?
I don't know if I've seen the video, but I've seen some of those figures you mentioned. I think there were figures much higher than that as well. Earlier estimates maybe of, I don't know, 25 degrees, 10 times the value.
Right. Well, the point I'm making. Welcome back, Bob. We lost you.
Yeah, I think my Zoom connection messed up.
All right.
Okay, because I want to ask you the question. Okay, continue.
Anyway, we're talking about the fact that Andre Assisi has pointed out there are multiple predictions of a temperature of the universe, if you will. It's a more vague, more general aspect of it. And since there are multiple predictions, many of them made prior, or lots of them made prior to the one made by Gamov and his group, why should we pick the one that Gamov came up with?
Yeah, that may be a good question. Were these other earlier ones well known or anything?
Probably not.
Yeah, well,
Okay.
mhm. And you say they're not entirely consistent, is that the claim also?
They didn't
Well,
pay much attention to them until it was first raised that um, this is one of the confirmations of general relativity. And then I think they looked at all these estimates prior, and they found the one which was close to what they wanted to.
That's cherry picking if you just pick the one that you like, which is something to watch out for. But yeah, well, whether that was actually going on in this case, I'm not sure because it's not clear how well known the other results were. But
well, what
Sorry,
really
I'm sorry.
happened was that Penzias and Wilson had an unexplained temperature in their antenna, and they were in communication with the other group at Princeton and who were working on these predictions of the Big Bang Theory predictions. And so when they said, "Oh, we've got this temperature in our antenna that we can't explain," and then the Princeton guy said, "Oh, that could be due to this Big Bang. Our Big Bang Theory can explain that," and that's how it came about.
yeah, okay. But something else may also be able to explain it soon. And
Correct.
usually it
That's
isn't
the point.
conclusive proof, but
Correct. Something else.
Okay. Can I ask you the question, guys? They done estimates. I don't know on what basis. If somebody calculated the temperature measured in 20 years ago, something like this, somebody calculated them because we are talking about predictions. Predictions must be not only exist, not exist. That's it. You must put some parameters of your predictions. Somebody put predictions, calculated temperature of cosmic microwave background radiation. Because what does it mean, prediction? Oh, it seems to me. But
Right.
physicists, it's not
That's
seems
a
to
good
me.
that's a good point. What does it mean, prediction?
Yeah. What does it mean, prediction? God
yeah,
exists or not? Okay, exists.
I don't
And
know if
from
anyone in general relativity was making the prediction prior to the observation here. Have you heard of
I'm
them?
talking about particular on a temperature of microwave background radiation. This is one of the main confirmation of Big Bang model. And I want to ask somebody from them calculated this temperature or not?
Before they had the observation? Not that I'm aware of, but
Even now, before prediction, no calculations, only estimates, and they found the closest estimate what they measured later. Okay, but when you measured it, please give me the theory based on this theory, Big Bang model. Show me that you calculated this temperature with the right value.
mhm. Yeah, it sounds to me like it was more like post-diction and figuring out a way where you get the right answer. But
Even post-diction, nobody, still now, nobody except myself calculated this temperature.
okay. Yeah.
All right. Can we
So
put
for
your
Big Bang model,
presentation? Can you put your presentation
I,
back up?
unfortunately I lost it when I
Oh,
lost Zoom, so I'm going to have to do let me see here if I can.
all right.
I have another question. This is Harry, sorry. Robert, I want to ask you this question. When I was a student long time ago, it was such a physical law for students. It means if you have some theory and you want confirmation of this theory, you must prove it on in all cases, not probable, not probable, in all cases. If you have even only one contradiction to your theory, forget about it because there is contradiction. It
Yeah,
doesn't
yeah,
work.
yeah. That's kind of over an idealized version or overstating things because nothing ever works exactly that way. It's impossible. You have an impossible standard. Theory,
Thermodynamics in physics, it's well developed. It seems to me there is no contradiction in thermodynamics or in mechanics or in something like this. I'm not sure with you, man, because
yeah,
I
well,
passed all these courses in physics, mechanics, thermodynamics, electricity,
yeah,
electrodynamics, all this stuff. They're consistent. I don't have any
well, hopefully, but even if
problems
there is
with
a
them.
contradiction, you have to work in trying to get rid of a contradiction. Doesn't mean you have to give up on everything.
But the contrary is true with regard to these modern theories, like general relativity or maybe quantum theory. I mean, what
Yeah.
they're continually saying to us is, look, there are countless experiments which have proved the validity of these things. They work in all matters. They on the microscopic scale, on the macroscopic scale. So if we find something that is contradictory, in other words, ostensibly proving them wrong, there must be something wrong with that. We're going to have to find some reason why that experiment was incorrect, or maybe we'd have to adjust some parameter because we know these theories are correct. They're like religions, they're infallible.
Yeah, yeah, that's a danger. Science shouldn't be a
You're
religion.
absolutely right, man.
Yeah.
You don't need confirmation. You have your religion and follow it. That's it. Simple like this. Guys, I will give you one example only. Let's talk about one example. So named speed of light. General relativity, special relativity. Many times I ask you, what does it mean speed? I don't understand as a physicist. What does it mean light? What does it mean speed of light? And light, what is it?
Okay. It means speed of light in vacuum.
Okay, in vacuum. Okay,
Okay.
good. It means only this one, in vacuum only. Because in Maxwell equations, there is electrodynamic constant C. And if you're going to any medium, the speed of electromagnetic waves will be different, and you must take into account electrical and magnetic parameters of the medium you're going through.
Okay. Yeah.
And a very good example, there are some, many times I named them, fast radio bursts. Fast radio bursts, it's a radio waves. And there is dispersion of these radio waves. There is a different speed of radio waves in fast radio bursts. And it's confirmed at least for 15 years, basic experimental results they conflict with the main proposal, the main parameter now they put in Maxwell equations, speed of light. I don't know what does it mean, speed of light. In the basic equations of Maxwell, there is speed of electromagnetic waves. There is
Okay.
no notion even light. And
Okay.
electromagnetic waves, fast radio bursts, radio waves, they have a dispersion because there is no vacuum, there is a medium, and you must take into account magnetic and electrical parameter of the medium. Simple like this.
Okay. Well, I want to make
One
a
contradiction, and you cut your Big Bang immediately because it's vacuum, but there is no vacuum. There is something around us. In my case, it's cosmic medium. You can name it whatever. Cosmic plasma, intergalactic plasma, it exists. They measured even what is the concentration of intergalactic plasma. How we can use speed of light notion if it contradicts to the basic physical experimental results.
Okay, well, I want to make a couple points. One is actually I am impressed that Maxwell was able to come up with C from the rest of his equations. I think that is impressive, and I think that confirms something. And I do kind of like Maxwell. Okay, that's one point. And of course, the real Maxwell actually he held a version of an ether theory. I don't know, as that always gets emphasized. People are always impressed that the Maxwell equations are invariant across all reference frames and things. Special people in special relativity, including my brother, they like to emphasize that. That's one point. A second point is I account for light in terms, I've gone into this a little bit before, in terms of fields, and I'm a realist about fields, including the electromagnetic field. And actually, I hold a version of an emission theory. So I actually hold that the fields are moved along with particles. So I don't even think it all depends upon the motion of the source. Now, actually, we have a little bit of time still left.
Not much. 5 minutes.
Oh, okay, why don't I make a point here? Because I was looking into this recently. This was actually an experiment in the early 1960s that Wallace Cantor performed. He originally did it in San Diego. He was working with the Navy, and they moved his apparatus to China Lake, which is also in California. In both places, he showed an interference fringe that he claimed confirmed basically Ritz's theory. And then what?
Oh, all right. We lost Bob. There's something wrong with Bob's system there. All right. We've got a few minutes here. We got 4 minutes.
I'm so delighted that my system seems to be working today.
Yeah, I'm gonna pressure Bob to do a presentation on this Cantor thing. We've had an exchange on Cantor and his Cantor's experiments. Cantor was an anti special relativity, and I read a number of his papers back many years ago. Okay, so we lost Bob. Let's see, what else? Any other comments?
Couple minutes. Can I talk for a couple minutes? Okay. He's good. He's back. Okay, good.
Yeah, I got cut off again, unfortunately. But yeah, I was talking about Walter Cantor, and I did have a correspondence with him once. He died like 10 years ago. But yeah, so he kept saying that, in fact, he did have a good experimental result. But when they tried repeating it, they claimed that it went against him, including doing the experiment in a vacuum. And he said, well, first off, when they did it in a vacuum, they used a different apparatus and things. And so it raises the question sometimes about an experimental result. Which ones should we hang on to? Which ones not? And I think there's a strong bias in favor of hanging on to the ones which agree with our theory and to discard ones that don't. And
It's
so, of course,
exactly
the
the
people
point.
here who were trying to replicate it, they held special relativity, so they got the result maybe they were looking for. And I don't really have a strong opinion about who's right or wrong there, but I was looking at it in some detail. I think maybe someone what they should have done was kept the same apparatus. One of his claims is that the person who did the refuting theory, he actually saw the infringement result, the interference result that confirmed the theory. But then he says statistically, the results went the other way. And sorting this out, I actually wouldn't mind investigating further. But there can
Well,
be a lot of sort of a bias here in terms of just hanging on to observations that you like for your your favorite theory.
right. Okay, we got 2 minutes. Bob, I'd like to hear more about this. Maybe you could do a presentation if you have the interest in
I
getting down.
would like to look at it in some more detail. I know, like Ed Dowdy, he knew Cantor. He also knew Peter Beckman. He seemed
All
to
right.
be more impressed by Beckman than Cantor. But again, it's part of it was Cantor held the ballistic version. I don't hold the ballistic version, nor did Dowdy. But yeah, there's more to say there.
All right. Tom Miles, do you know about Tom Miles?
No.
All right, not Tom Miles knows a lot about Cantor,
Uh-huh.
and he's also a proponent of the ballistic theory. And so I'll try to send you his email, and I haven't heard from him in a while. I think he may be declining in health, but he first turned me on to Cantor many years ago. I didn't know about Cantor, and he told me about Cantor. So maybe he can help you there with some
Yeah,
information.
I know Cantor also questioned the longitudinal Doppler shift, and has a critique of that.
All right, we're
I
coming
mean
up here less
transverse,
than a minute.
transverse Doppler shift.
What?
What do you
Transverse
mean
Doppler shift.
transverse?
Transverse Doppler shift, the
Yeah, he said,
relativistic one. Yeah,
yeah.
he questioned that, or
Yeah,
experiments confirmed it.
you sent me an email on that.
Yeah, yeah.
Um, that's basically boils down to being time dilation according to Einstein.
Hmm.
It's measuring time dilation and a signal that's going transverse to the device.
Yeah.
And to me, that's another example of post-diction. I think Einstein knew about this. Came up yesterday. Einstein. All right. Well, we got Bob back.
Yeah, hopefully it'll stay. We'll see.
All right. I was running my mouth there. Um, all right. Did I approve? Um, did you send me a
Well,
report?
we lost them all. I think you're going to have to send me another request for the slides.
No, I'm talking about. Are we recording,
Yeah.
Roger?
Yeah. Okay.
All right. Okay. I have them here. I can share my
Yeah,
version of it.
that would be fine.
Um, oh, uh-oh. Okay, that's my version of it. I'm not sure if I should get rid of the stuff on the side. All right. I did, there's a whole bunch of issues that you can bring up here
Oh,
um,
absolutely.
on these
Absolutely.
topics. Like it is always possible to save any non-contradictory hypothesis, no matter how bizarre, if one is willing to make enough adjustments. Uh, you know, I think Ian brought this up. What if it's a contradictory theory?
That's why I have non-contradictory in there, but even with contradiction, sometimes a theory has a contradiction that's it's not really inherent to the whole theory, and there's an internal way to get rid of it. That's not unknown.
All right, let me just mention this. I'm not really sure if you're familiar with this, Bob, but my friend who's a professor of religion says that in the Western tradition, there's an idea of um, a philosophical idea should be non-contradictory, but he says that idea of contradiction being refuting an idea doesn't exist in Eastern religion and Eastern thinking.
You may
Are
be
you?
talking about Taoism, like yin and yang.
Yeah,
They're
that sort of
contradicting.
thing. Yes.
Yeah. Or at
Are you
least
aware?
opposing. You can distinguish between opposing forces and actually having a contradiction. I think yin and yang is more opposing forces.
Right.
But
Well,
also that
his
they could simultaneously hold different views. Like they were telling me when I was in China, oh, we have a basic primitive animistic religion, and then we have Confucianism, and we could even have Christianity. We could have all the religions. Whereas in the West, we say, well, if you're not a Christian, that's it. You cannot hold Christianity and another religion. We're sort of exclusive. But they can
Well,
hold simultaneous various
I
religions.
mean the same person. Actually, I've run across some people I even hear they just like to go to church and they go to different churches and they're more
Yeah.
interested in going to church than any claims the church makes. So I've run across that before, but
Yeah, but I'm more concerned with the idea of that a contradiction doesn't really like special relativity, in my opinion, is the ultimate example of a theory that's contradictory that ignores the contradictions.
you're thinking of the twin paradox there, Harry.
Well, there's lots of paradoxes in special relativity. The twin paradox is just the most famous one, the one that's got the most publicity. You know what I'm saying?
Hmm.
We talked the last time, of course, about getting a synthesis from contradictions, thesis and antithesis. And
Right.
I suppose Kant did that as well from his antinomies. You get the opposite. But you do not hold simultaneously these contradictory hypotheses. You use them maybe to get a more correct hypothesis, which has certain elements.
Right. That's the process of the dialectic. And
Yes.
actually, Hegel wasn't the first to talk about
It was
dialectic.
Fichte, I think.
Yeah, no, actually, Plato has a dialectic,
Yeah,
Right.
yes.
and Kant he has a dialectic, and they don't all mean exactly the same thing. For Plato, it's more like conversations going back and forth, and for Kant, it's the section after his analytic, and but it is sort of on problems, including the antinomies. Does space have a beginning or not? Things like that. and you run into problems no matter how you answer, and those are the antinomies.
Okay, but the reason I brought this up is there's no, I mean, other than special relativity, there really isn't any mainstream scientific thought that just ignores contradictions. Contradictions are a theory killer, correct?
They should be, or so you got to at least get rid of them within your theory if you don't move on to another one. Yeah, but contradictions are false, so there's something wrong. Yeah.
Right, but not in the case of special relativity.
I mean, the people holding this, and they're saying, I do know some people who like special relativity, and they'll claim that there's not a contradiction with the twin paradox and things. I've definitely run across that. But again, that's not my position. I'd rather some of these people, I really wish there was more dialogue between people who hold special relativity and people who don't.
Well, but the Quinn-Duhem thesis is that I can always come up with um, um, auxiliary hypotheses that remove the contradiction or avoid it.
Well, yeah, for any, I deliberately said non-contradictory hypothesis, you can always do it.
Well, okay, so I claim that special relativity is contradictory, and these other people claim no, it's not because blah 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 blah. Okay, they introduce an auxiliary hypothesis that avoids the contradiction. That's what they do in the twin paradox, basically.
Well, I do know some of them at least talk about the twin paradox because I've come across that. But yeah, whether what they say in any sense holds up, again, I'd rather they would speak for the theory rather than me. But
well, my point is, I think that's an example of the Quinn-Duhem thesis, which is that and there are so many paradoxes and contradictions, but well, they call them paradoxes because they don't want to use the word contradiction because that's too deadly. A paradox is only a seeming contradiction.
Yeah.
Right. It's only, it only seems to be a contradiction. It's not really a contradiction. And of course, then the next step is to tell you the auxiliary adjustments, the adjustments or additional assumptions that are brought into the picture that supposedly negate the appearance of a contradiction. So that's
and frequently they dismiss it by saying, well, it appears to be a contradiction, but that means you'll have to change your conception of common sense. You've got the wrong ideas and we'll have to modify that. Whereas in the Grecian system of logic, you would prove something by contradiction. If your hypothesis led to a contradiction, you say, right, therefore the hypothesis is incorrect. But here they're saying, no, you'll have to modify your conceptions about what is contradictory.
Yeah, I'm not even sure they're using contradiction the same way. Like Hegel uses the term, but you look at his actual examples and it's more like opposite, opposing forces rather than logical contradictions. And I think the same thing is going on with Eastern philosophy. Maybe I'm wrong, but I think it is.
Okay, but my point I'm making is that mathematics works largely on the principle that you can't have a contradiction. So in other words, a lot of theorems are proved by showing there is no if there is a contradiction, then they say they make the opposite assumption and then prove there's a contradiction, and so that
right. That's the method of reductio ad absurdum. Yes, yes.
Right, and mathematics is largely based on that.
Well, it's certainly one of the big methods used. Yeah.
And well, the really important stuff is really based on the principle of contradiction. Yeah. So we have this problem if you're basing your deductions and your mathematics on the principle that there can't be a contradiction, then when you have a theory that produces contradictions, which you essentially say are really paradox, they're only seeming contradictions. I mean, to me, that seems to falsify the concept right there.
Yeah, no, you're right. If it's really a logical contradiction, that proves there's something wrong. Yes.
But it's a whole different conception of what is contradictory. I mean, in Euclidean geometry, you might prove that two triangles are congruent by saying, okay, here's one triangle, move it so that the apex of this one fits on the apex of the other one, and then because the angle subtended there is equal, the two sides will fall on it, and the length, and so on. You can do that, but you can say straight away, no. In special relativity, if you move that triangle onto the other one, it would diminish in length. There'd be length contraction, so you cannot even prove that. So it's a whole different conception to the Grecian sense of logic.
Hmm. Yeah. Well, it's also maybe different from the Grecian sense of space. And well, it's a good question what sense of space they were actually using, whether it was physical space or a more abstract sense of space.
An idealized physical space, I suppose.
Maybe.
Well, I know that there's arguments about in special relativity about Popper, and Popper got involved in special relativity, where he talked in particular about the contraction hypothesis, and he objected to the Lorentz Fitzgerald hypothesis and claimed that it was an ad hoc hypothesis and therefore was invalid. I don't know if you're familiar with that or not.
To some extent, I've come across the claim. They usually bring in Fitzgerald with Lorentz and say that that was ad hoc to explain the Michelson-Morley
Right.
experiment. Yeah, and I know, like, let's see, Bohm, David Bohm, he said that Lorentz's version was ad hoc, but not was not ad hoc, but Fitzgerald's was because Lorentz he actually builds a whole theory, a bit of an ether theory into his account as well. But whether how much of that he had before he knew about Michelson-Morley, I mean, maybe that's a good question. But if you put it in just to explain something, that's basically the meaning of ad hoc for a particular purpose.
Right. I just brought that up because I wanted to mention that Popper did get involved in that, and
Right. But also Popper, basically everyone I knew at Boston University, I mean, they all liked special relativity. As a matter of fact, John Statcher, who was in the physics department, I knew him some. They were editing the Einstein papers at Boston University. So the people there, they seem to all like Einstein and special relativity.
You're talking about
It was
Stachel?
Shimoni who first told me about emission theories, and I actually talked to someone over in the astronomy department who'd done some stuff on emission theories.
Okay, I'm sorry to interrupt you, but I didn't hear. Who did you say that was editing Einstein's papers?
John Statchel.
Okay, that's
He
who
was
I
in the
thought.
physics department.
Okay. I didn't realize that. I know. And excuse me for coughing. Yeah, well, I'm not really sure that those people are really. I'm not really sure that I'm not sure that they really understand the dissident viewpoint and the arguments of Dingle. They've basically been, they bring in these ad hoc arguments, or the auxiliary hypothesis, if you will, to sort of negate Dingle's arguments, and they protect special relativity by the bringing in the auxiliary or additional assumptions, if you will. It's really the additional assumptions is that there's really no absolute time. So since there's no absolute time, then you really can't pin down an argument as to whether something is a contradiction or not, because you don't know what time really is, because of the relativity of simultaneity. And so any proof that proves that there's a contradiction is wrong, because the relativity of simultaneity is not taken into account. So it's a beautiful theory full of self-protecting auxiliary.
Yeah. Well, what Popper calls that is immunizing a theory against refutation.
Right. That's exactly what they do.
His example he liked to use was actually psychoanalysis on it. But and of course, Popper liked special relativity, but
right, that's the irony of it.
Yeah.
I'm always amazed. I've stated this before that notwithstanding the differences in approaches, we talked about the difference in ideas between East and West ideas. It's been so pervasive, these systems and saving modern theories. Doesn't matter whether you're in the East, in the West, in a Marxist society, in a capitalist society. Doesn't matter. It's all over the world. They're thinking exactly the same way. You go to your academic institutions with some of your philosophers there. They like special relativity as well. Um, you know, it's so pervasive. It's become international, a worldwide religion. Again, I use the term perhaps something that binds people together. There's no, if it's not a contradiction in terms, there's no orthodox dissidence. The dissidence is small groups like us coming out and saying this, that, the other. There's no school of dissidence, which is the
Well,
mainstream in any
we don't
kind.
agree among ourselves as among, well, maybe it's a problem. Yes and no on being a problem. Actually, I think we should work more among ourselves for and improving theories to the extent that there's common content. There isn't even always common content.
Okay, I wanted to comment on post-diction versus prediction. Um, I noticed that Beal brought this up yesterday, but I have mentioned in my previous talk where Einstein was aware of this transverse Doppler effect. You know what I'm talking about. Stark did these experiments and
I
using
know
magnetic.
Stark, but what I know with Stark is the Stark effect with a spectrum where you have a broadening out of spectrum lines in an electric field. Uh,
That's not what we're talking about. But
yeah, I know, but maybe Stark did work in more than one.
right, he did these experiments, and he um, they were, and I think they came out prior to. I'm not sure whether it was prior to 1905, but I think it was in 1904. So not only was Einstein aware of the Lamour prediction of time dilation, but I think he was also aware of these experiments that had been done by Stark that predicted a redshift of these transverse moving Cantle rays.
Right.
So you understand what I'm saying?
Yeah, okay, so it's a post-diction. Also, there's some other things I'd like to know the history on better, including like mass increases with increased velocity, when that was first learned about, whether that's also like a post-diction for Einstein.
I
Well,
think
actually,
so.
Lorentz talks about that one also, but whether it was a post-diction as opposed to a prediction.
I think that's also the case.
I
And
think
E equals MC squared, the most famous one, that's post-diction.
Yeah, that had already been.
You know that.
Well, there were some people who, yes, well, we know about that. Yes,
Well, I know some people credit Poincaré for that one, but
correct. There's a
Poincaré dealt with it, but it goes back to Newton actually.
uh-huh.
More recently, other people had like 3/4 MC squared. People like Hasselhoff.
I see.
Isn't E equals MC squared just simply dimensional analysis?
How so?
Well, energy has the dimensions of mass times velocity squared.
Yeah, at least kinetic energy. Yeah.
well. I think this is all. I guess my point I would make here is that's a good point, Jim. My point I would think is that it's better if you're an advocate for a theory that's on questionable foundations if you can amass all of these great things that he has predicted. Okay. You can say theory of relativity predicts all these great things, but it turns out they're mostly post-dictions.
Hmm.
And then the other thing you pointed out is you know accepting results which are in accordance with what you want to believe. So it has been said, for example, that when you do an experiment and you get results which you expected, You trust your equipment. You never go back to say maybe there was something wrong with that result. No, it's fine. But when you get a result which is contrary to what you wish to get, you said there must be some problem with my equipment, and
Right.
you look into great detail to see was there something wrong with it. Well, you should do that in all cases, even when it gives you the correct results or the results you wished.
Well, yeah, you're absolutely right there. I know I have actually worked a little bit in some laboratories, and I'll be the first to admit I'm not that good of an experimentalist. But there are all sorts of ways where, I mean, maybe something isn't as clean, say a mirror as it ought to be or something, and then you get various bad results, and then you get a good one, but maybe it just happened by basically by coincidence. The good one, that's the one you cherry pick. There are all sorts of things you have to watch out for.
That's it, yes.
Okay, do we have any more comments? Oh, okay. So I have an issue with the presentation that occurred yesterday, and my main issue with it is if you find mistakes in Einstein's 1905 paper, does that negate his theory?
Negate, how are you using the word negate?
Well, falsify or disprove or
Rule
Well,
out.
it might negate his way of deriving it, but I don't think per se it negates the theory. And I don't think Beal would be the first to say that.
I know this much, and I wouldn't mind looking at this in some detail if I could get a copy of his paper. I don't like having to pay money for a copy of a paper. But what I like to do with math, the mistakes and things, is I wish people wouldn't skip steps. I know it makes a paper longer, but I can follow it, and I'm not a great mathematician, so I like to know where each step is coming from, and then I can see if I can make the derivation myself. And so checking his work, and if it really checks out, then yeah, it shows that there was a problem with the 1905 paper, which wouldn't surprise me.
By the way, he did send me a courtesy copy of his published paper in Physics Essays, and I didn't send it out to everybody because I was a bit afraid, that wouldn't be the right thing to do. However, I'm quite willing to send it out to anybody who wants it. I'll send you one, Bob, if you
Yeah, I'd
wish.
appreciate it. Yeah.
Yeah.
all right, I'd
Otherwise,
like
it's
to
like
see that too.
$40 or so to get the paper.
Yeah, no,
All
I
right,
can.
here's a, okay, I understand. Why don't you do that? I'd like
Anybody else
one.
wants it, I'll send it as well, Harry. You
All right.
probably ready.
I did want to comment on this. Bob, the original 1905 paper is on the internet. I got confused. I thought you were referring to that. I think not. The book that he referred to. Now, I knew about this book. It's by I can't remember his name. A.I. Miller. A.I. Miller, and um, that book gives a more detailed explanation of what's going on. That's sort of as an attempt to try to fill in the steps that you're talking about that Einstein did in his 1905 paper, but without some kind of guide or explanation as to what he's doing in his paper, it's almost impossible to make sense out of what he's doing. And that's one of the big problems with referring to the 1905 paper. And because it's just, unless you have a book that explains to you or some other person who's analyzed it in detail, it's incomprehensible.
Yeah, I could never follow the math on it.
Right. I never could either. And but this book by A.I. Miller, Einstein's Theory of Relativity, I think is the name of the book by A.I. Miller. He gives an explanation of the details, and it's a pretty detailed book. So I noticed that he had a copy of that book. So yeah.
Right. But Beal is making no bones about his contention that Einstein knew about the Lorentz transformations. Obviously, they'd been around, and he wanted to establish that they were the correct transformations, and he went about it in this strange way with these parameters, which he went through. And he said he made mistakes, and so it was obviously post whatever post hoc or post diction, whatever
I
you call
know.
it.
I know in one place Einstein denies it, but what convinces me he knew it is Einstein uses beta, not the way they do it today, but he uses it the exact same way that Lorentz does, and they both use beta for the same thing.
Right.
Right.
Well, yeah. Okay. Let's see. The other point that I wanted to make was that he had the wrong time dilation equation. And in 1905, the time dilation equation is what I call the coordinate. Well, it's the inverse basis transformation in my terminology. But they changed it he changed it in his later papers. And it's the transformation in the later papers that you're going to find in the textbooks. And the fact that he didn't mention that, I thought was kind of glaring. So you can't really base everything that you say or criticize about Einstein based on his 1905 paper. I think that's a problem right there, because he changes things as he goes along, and he never really produces this is my theory of special relativity. He never really does that. The closest he gets is this 1912 manuscript that he writes that never gets published. He never finished it.
Mhm.
Well,
He never
all of
says
that
that he's
contributes to
changing
the
anything.
fact that this would make Einstein's work a perfect tool to use to prevent advances in science. And the nation or geopolitical bloc that wins in the end is most advanced in science and technology. So that what you want to do to be that winner geopolitically is to prevent advances in science by having people all over the world waste all their time talking about length contraction and time dilation and so forth, and the hoax of the Lorentz transform, so that they will not make advances in science. They'll just be going around circles forever.
Well, they've done that, but what really the issue here is that Einstein's theory is really a metaphysical ideology. What he talks about in 2005 in his papers is really metaphysical ideology. And it's really Minkowski that does the mathematics. So if you want to criticize the mathematics to a certain extent that's currently being used and accepted, that's in the advanced textbooks, that's Minkowski's theory, not Einstein's theory. And what they did is they grafted the metaphysics of Einstein onto Minkowski's mathematics, and kind of kept some of his fundamental formulas, like, for instance, the time dilation formula. I use the word fudge. They fudge in space-time Minkowski mathematics. They kind of fudge the answer to agree with what Einstein says, but it's mathematically a different theory. Anyway, that's my little spiel on that.
But Beal, of course, derived another equation on his own analysis, which gave you something like 24 million times the time dilation that the original Einstein.
I don't think he understood what was going on. I think he completely misunderstood what was happening, because what is happening is that in the one section, he derives the Lorentz transform. And then there's a kind of a transition where he talks about x squared plus y squared plus z squared equals c squared t squared, and talks about the Lorentz transformation.
Well, that's just the length of a vector. The square root of that is the length of a vector.
That's Minkowski's theory. And so then he goes into the next section where he talks about the consequences of this theory that he's developed. And what he's doing there is he's taking the Lorentz transformation that as a given and then deriving consequences. What Beal did was he took equations from the previous section that were not really related to the Lorentz transform and then tried to put them into the Lorentz transform and got a different time dilation equation. I don't think that was valid. I think that was just a mistake on his part. And he asked the question, what is X? And, I think he just got confused. Anyway.
Yeah, I did not understand when Beal said that X equals CT. Does anybody have any way to enlighten me on that? That seems like a strange thing to write down.
He just pulled that out of a previous section.
Yeah.
That was an equation that applied to a previous argument.
And he said X dash over C minus V equals T. But that seems to follow from Einstein's derivation.
Anyway,
what they're doing is abusing T, as in using it both as a dependent and independent variable at the same time. That's a no-no in science. When you have a velocity in your equation along with a T in your equation, you're using time 2 times. And then you start, a recent quote that I heard in one of these sessions was, a clock moving at velocity v. Well, the clock you're using T again in even defining what a clock is. So this is an abuse of science, 7 ways to Sunday, and there's no way out. You either have to have T as an independent variable or not.
I already solved this problem in my presentation that I gave on correcting Einstein's math. So that's not in there. That problem doesn't exist in that.
Well, T is used as a position coordinate in the Lorentz transform, and I believe you were talking about 4 versions of that.
Yeah, but they're not functions of each other like in special relativity.
Well, that doesn't pertain to my argument that T is used as a position coordinate.
And in my theory, it's not. It is in special relativity. That's correct. In Minkowski's theory, yes. In the 4-dimensional space-time.
So you're using
I consider all
Euclidean
this
theory.
bother hardly worth it, because it's really the Lorentz transformation, as far as I'm concerned, is basically and similar transformations are just quick mathematical tricks to try to resolve a problem that is actually resolved physically. Namely,
well, it works out in the it works out as in doing equations for relativistic particle accelerators, and they get the correct predictions.
yes,
and
so
they
that's the thing.
design particle accelerators correctly using the Lorentz transform.
So a lot of us have been, Harry, subjected to the statement, well, even if it is a bit wrong, Einstein's theory, what are you going to put in its place because it's been so successful? Now, Beal,
I already proposed such a theory. Weren't you here for those presentations?
Yeah, okay, your modified theory. But Beal, I mean, just generally, Beal said, I've nothing to put in its place. He said, I'm just pointing out the errors. He doesn't go as far as you.
Yeah, that's the reason why dissidents are ignored by mainstream.
Well, it's not that we don't have anything to put into place, but we each want to replace it with something different. So
we do. We all have different. Maybe we're leading towards the same end. I don't know. I mean, my system is I'm using a classical fluid dynamics analysis to replace it, which possibly would have been done by others had people like Einstein and maybe Poincare before him, or maybe Lorentz.
By
maybe
fluid, are you including gases and liquids, or one or the other, or what?
Yeah, I mean, sometimes we talk about hydrodynamics, but very strictly speaking, that's concerned with water.
Yeah, you need it in a broader sense. You don't have to have water, but I like the concept of an ideal liquid. And I know there are people who throw around ideal gases. I don't buy into that, or ideal solids. But I've made the most progress with ideal liquids.
Yeah, but they would have viscosity and so on. It's just they would be. Would they be what we might sometimes call Newtonian liquids rather than non-Newtonian liquids?
Maybe,
Yeah.
depends on,
Yeah. Okay.
yeah.
Because
But
non-Newtonians, you have weird things like thixotropic liquids and things like that.
yeah, no, I have no viscosity, so no friction, but
Okay, well that's okay. So that's what you mean by ideal, yeah.
yeah.
Okay.
And it can be split into parts and recombined and things, which is what I think happens all the time, like with light.
Yeah. Well, I'm including a lot of these parameters actually into electromagnetic radiation, or at least analogs of them.
Yeah, we
I
might
have
have
sort of
something in
almost an
common then.
analog of viscosity, actually.
Yeah.
All right, we got 4 minutes. You want to make a summary comments, Bob, or?
I don't know if I can really. I was saying what I'm saying is actually, as far as method goes, this is pretty mainstream, except that some people like they either emphasize confirmation or refutation, like Popper, and I really think you need both. I think you should try to make bold hypotheses, make bold predictions, and try to refute them, like Popper says. But I think there's also something to be said for confirmation, but it's never conclusive confirmation. It's some variant on Bayes' theorem there that you increase the probability of your theory being true.
The interesting thing I might submit is that your principles would generally be agreed. I mean, if you got scientists, mainstream scientists from all over the world, I'm sure they wouldn't disagree. They wouldn't say you should be ad hominem to people or you shouldn't use, correct deduction and so on. They'd agree with everything. The biggest transgressors of your principles would agree in principle with them. It's like a hypocrisy, I
Yeah,
would say.
yeah, yeah.
Except when it comes to climate change.
The climate change people who are probably the biggest transgressors of these principles, that's correct, would not dissent from them if you put them up against it.
Right, exactly. It's the irony of it.
Yeah.
But remember, 97% of them have the same opinion.
Right. That makes it correct.
Yeah.
All right. Well, thank you, Bob.
Yeah, sure, yeah.
Let's see. Do we have any? We got 2 minutes for any final comments. No final comments. All right. Well, I think that one of the issues is that if we wanted to apply some of these principles to a particular argument that's being made, we could find a lot of holes in established scientific arguments. Of course, we focused on special relativity. I brought up climate change. There may be other areas where we might find contradictions. Do you have any thoughts on that, Bob?
Oh, I'm as interested with that special relativity. Well, also quantum mechanics. Quantum mechanics in time seems to embrace something close to contradictions, like with the Copenhagen approach. And also, it's not always physically realist. And I think there's an awful lot to be said for physical realism.
I didn't. We did talk about cosmology and some of the issues in cosmology. We did talk about that. So that's another area where it looks like there's contradictions. Okay. I want to thank everybody for coming today and participating. Bob, good job. And we'll look forward to you talking about Cantor
Yeah,
at some point in the
at
future.
some point, yeah. Okay.
I want next week is open for somebody if you want to have a topic that you want to discuss and present on that. That's open. Otherwise, I will be talking about Einstein's mistakes and correcting his math because there's a lot there to talk about.